In this tutorial, we're going on with our series on complex numbers. And in this video, we'll have two examples on how to factor complex trinomials. In our first example, we have w squared plus 8w plus 20. And what we notice right from the start is that we cannot apply normal trinomial factoring. So we would need to use another method. And we are going to use completing the square. So if I rewrite that expression, I have w squared plus 8w, and then to complete the square, I focus on the coefficient in front of w. So I'll add half of that coefficient squared, and I'll subtract half of that coefficient squared. So I add and subtract half of the coefficient of w, which is 8 squared. So it's plus 4 squared minus 4 squared. Now what I've created is a perfect or complete square in my first three terms. So I can apply normal factoring, which would be w plus 4 times w plus 4. That product would lead to w squared plus 8w plus 4 squared. And then I can bring down the negative 16 of the 4 squared plus 20. So if I rewrite that slightly, I have w plus 4 in brackets squared plus 4. And again, we notice that we cannot factor further because this is not a difference of two squares. But with our understanding of complex numbers, we can rewrite the plus 4 as negative 2i squared. So we have w plus 4 squared minus 2i squared. This now is a difference of two squares which we can easily factorize. So when I factorize, I have w plus 4 minus 2i times w plus 4 plus 2i. And that is how we can factor this trinomial. So first we completed the square to create a complete square or perfect square that we can factorize. And then from there, we rewritten plus 4 to be negative 2i squared, which led to a difference of two squares, which we could easily factorize. So let us look at another example. Let's say we have 4z squared plus 12z plus 13. And again, we cannot apply normal trinomial factoring. So what we need to do is again apply completing the square. But for this example, I want to show you a slightly different method. So we cannot simply take 12 divided by 2, which is 6 squared, and add 6 squared and subtract 6 squared, because we need to consider the impact of the coefficient in front of z squared. So normally what you would do is take out a greatest common factor of 4, which leads to z squared plus 3z plus 13 over 4, and then use the coefficient of the middle term to complete the square. But I want to show you something slightly different. What we are going to do is we're going to focus on the coefficient of z, which is our middle term, and we are going to divide that by 2 times the square root of the coefficient of z squared. So what it looks like is we have the coefficient of z, which is 12, and we are going to divide that by 2 times the square root of 4, which is the coefficient of z squared. And that leads to 3, because we have 12 divided by 2 times 2. So 12 divided by 4. So instead of taking out the greatest common factor, I'd have 4z squared plus 12z plus 3 squared minus 3 squared plus 13, where the 3 comes from taking the coefficient of z and dividing that by 2 times the square root of the coefficient of z squared. Now our first three terms is a perfect square which we can easily factorize. So that will be 2z plus 3 times 2z plus 3. Then we have minus 9 plus 13. And if I rewrite that slightly, I have 2z plus 3 squared plus 4. And again, I cannot factorize further, but I can rewrite plus 4 to create a difference of two squares. And I'll rewrite it the same way we did in our previous example, by writing plus 4 as negative 2i squared. Remember that I is the imaginary number of the square root of -1. And I squared is equals to -1. So if I use that principle to rewrite +4, I will have a difference of 2 squares as 2z plus 3 squared minus 2 times I squared. Now I can factor my difference of 2 squares. So that leads to 2z plus 3 minus 2i, closing the brackets, times 2z plus 3 plus 2i. And that's a simple way for us to factor trinomials while using the imaginary number.